because it is a non-linear system with memory. Non-linear because of the phase detector, with memory because of the filter. And generally speaking, the nonlinear system with memory is difficult to study. It is difficult to study by the analysis, from the analytical point of view. What one can do is to make experiments and to characterize some figure of merit of the PLL during transients. A transient occurs when the PLL, for instance, starts from scratch and attempts to lock the incoming sinusoid. Well, at the startup, the error will be not small, okay? So basically, usually, there are a couple of measurements that can be done on the nonlinear PLL to characterize it. One is the hold-in. The hold-in is the maximum frequency step that the PLL can track, still locking, that is remaining locked to the incoming sinusoid. So this means that this is the frequency ramp versus t, the incoming phase, theta. This is what happens by increasing the frequency step. The PLL will track the input frequency step, then we say that it is locked. But when this error is too big, then there is the sync loss of the cycle slip. And so, with a frequency step like this, what can happen is that the PLL cannot track it. Okay? So this is the sync loss. The maximum frequency step that can be tracked like this. This is phase lock. This is the input, this is at theta. It is difficult to find the hold-in range by analysis because it depends on the specific phase detector. So something can be done with a phase detector that is a sinusoid. In that case, there can be some chance of studying the nonlinear behavior of the PLL. But in general, one makes an experiment like this. Another figure is the capture range. Capture range is the maximum difference between the incoming sinusoid and the natural frequency of the VCO, of the NCO, that can be recovered by the PLL. So if the natural frequency of the PLL is F0 and the input frequency is F1, one computes this modulus, and then putting F1 at the input, two things can happen. One is that sooner or late the PLL locks the input sinusoid, and the other is that sooner or late, but anyway, it never locks the input. If it doesn't lock the input, then the capture range, the difference is outside the capture range. If it locks, then the difference is inside the capture range. Also, this figure of merit must be measured. That is, you build your phase detector, your PLL, and then try. And what about the performance of the PLL? Well, in general, you measure the performance by the mean square error. And till the error remains small and the mean square error is small, well, it works, the mean square error as a performance measure. But when errors start to be large, the mean square error is no more a good performance measure. Because what happens is that cycle slips appear. What is a cycle slip? A cycle slip is this. Here is the time, here is the theta. Suppose that this is the input theta. This is 2 pi, 4 pi, okay? And this is the recovered phase. Then at a certain time, for instance here, there can be a cycle slip, which means this. So the recovered phase tracks the input phase up to a certain instant. Then there is a temporary phase lock. You see, during this time, there is a temporary, sync loss. The recovered phase does no more track the input phase. And at a certain time, the PLL locks again, but with an error of 2 pi. Okay? This is a cycle slip. You see, here the difference is 2 pi, here the difference is 0. Remember that the input-output characteristic of the phase detector is periodic. Often the period is 2 pi. So if there is a difference of 2 pi between the input and the recovery phase, you say, okay, it is tracking. It is at the phase lock, everything works. Here there is a difference which is 0. Here 2 pi. What happened? Well, there has been a certain time interval where the synchronism is lost. You see? This is the cycle slip. When cycle slips start appearing, the performance of the PLL is destroyed. It is a phenomenon that is like the errors in the demodulation. Basically, the PLL can be used for frequency demodulation. If after having locked the phase you make the derivative, then you get the frequency. So, in the case of frequency modulation, you can use the PLL to demodulate the information contained into the frequency demodulation. Well, these cycle slips sound like clicks when you use the FM, the frequency modulation, for transmitting audio signals, as with the radio, as with the FM radio, and the reception is not so good, you start hearing clicks that are psychosleeps. Yes, please.
I didn't understand if the psychosleep is the part where
No, the psychosleep is the plus 2 pi. Plus 2 pi. This is the time window where the type psychosleep occurs. Okay. With the FM, you have an input signal like this, and you want to recover the derivative of the phase. That is, you measure the phase along time and then make the derivative. Okay? And so this moves in some way, randomly. And the recovered, the demodulated phase can be like this, and then tracking it along time, like this. Okay? Or like this with some small error. What happens when, due to the noise, the amplitude of the input becomes small? It cannot no more be tracked. So if at a certain time instant the input signal is like this, you know, it becomes difficult to measure the phase. And when the noise disappears and it becomes again big, well, you can lock it and the phase measurement at the point is good. But what about what happened during the time region when the input amplitude was small? Who knows? What happened to the phase? It cannot be tracked. It cannot be locked because it is too weak compared to the noise. And in the phase can happen something like this.
What is the problem of this phase ambiguity? Because the derivative is the same of the two.
No, the derivative here is not the same.
In that portion, not, but when
Yes.
after that it's the same, so
Yes.
there's no problem.
Yes.
Yeah.
It happens that if you use the mean square error as a performance measure, well, it is not appropriate because the mean square error in some sense assumes that the noise, this difference between the input and the recovered signal is a stationary process. Okay? While here there is a big difference in the statistics of the error compared to what before and what after. Here there is a time window where the performance is very, very bad, while in the rest of the time the performance is acceptable. And how to say this? You cannot express this with the mean square error, because this can be also an event which that has a small probability. Anyway, when this happens, it means that the performance is really bad. Even if this happens with a small probability, it is like the probability of error. You can look to the signal to noise ratio, okay? But anyway, even with a probability of error of 10 to the minus 8, which can seem very, very, very low, in many cases the transmission system is out of order, is not on work. So even if this happens with a small probability, this cannot be accepted. It is a sync loss, while the PLL has to work in a phase locker condition. Okay? Questions? Do you see this phenomenon? Is it clear? Suppose that here, at this time instant, the input amplitude disappears. It has a phase, the input has a phase, but it has an amplitude which is so small that you can virtually say that it disappeared. And how can the PLL track the input phase? It can't, because there is no more input. And when the input amplitude appears again, you start again tracking, but actually you cannot know how many multiples of 2 pi of difference there are between the input and the recovery phase. Okay? Because it's like to say that this vector is wandering around the zero. How many cycles? You cannot say. It is a cycles limit. Okay? And another fact that I must mention is the use of PLL for frequency conversion. This is the digital PLL. Where the input and the output both are square waves. You know, a square wave is like a clock. What is called clock in the technical language. It's a sort of sinusoid, but actually what you find is this. In place of having a sinusoid, the rising and the falling edges of the sinusoid are rectified. Okay? This is the square wave. In the case of square waves, assume that they take their values into the set plus or minus 1. Okay? Minus 1, plus 1, and here there is the 0. The error is y by v. So at the phase lock, this is the input y, the output v is this. So the error has a 0 mean, okay, and the rising edge of V is exactly in the middle of the hold of the plus 1, let's say, of Y, and the falling edge is in the middle of the minus 1 of Y. So the error here is positive. Then negative, positive. This is the error. Really, it is not small, but what matters is that its expected value is 0. So when you put an error waveform like this into a low-pass filter, at the output of the low-pass filter you find the expectation in the end, and the expectation is 0. Okay? And so the PLL continues producing this V, which is phase locked to Y. Phase lock with a phase difference of half pi. This is exactly half pi, okay, in terms of phase. There are like two quadrature sinusoids, the cosine and the sine, okay? They are orthogonal, so the expectation of the product is 0. This is the say, digital version of the PLL. Digital means that the input is not a sinusoid. The input Y is not a sinusoid. It is a clock waveform. In this form, the PLL is used for frequency conversion. Let Phi be the frequency of the input clock and Fo be the frequency of the output clock. We can convert the frequency Fi into Fi by P over Q, getting Fo. Basically, if this is the clock at frequency Fi, we divide it by Q, frequency division. Here I mean frequency division. Then put it into the phase detector and the low-pass filter, the VCO. Here you have the sinusoid, rectify it and get the square wave, and then divide by P. Here the frequency is Fi divided by Q. Here it is Fo divided by P. And at the phase lock, these two frequencies are the same, because if the phase is locked, then of course the derivative of the frequency, which is the derivative of the phase, will be the same. So Fi over Q equal to Fo over P. Now get this as an output, the output frequency. Do you know how to perform frequency division? You get a clock as input. At frequency
Count the number of the clock.
count, exactly. This is basically a counter, and when the counter reaches Q, then it gives out a rising edge.
Yes.
This is a counter modulo Q. This is frequency division. For instance, frequency division by 2. Suppose you want to halve the frequency of an input clock like this. Then count 1, 2. This is the result of a modulo 2 counter. Okay? 1, 2, down. 1, 2, up. 1, 2, down. Okay? And the counter is a very, very simple electronic circuit. You can build it with, in this case, with 2 flip-flops. This will be a counter modulo P. And you see, in this case, FO is said to be synchronous with Fi because it is derived from Fi by frequency division in this way. So it is exactly, I don't know, 3/4, for instance. If P is equal to 3 and Q equal to 4, you get here a frequency that is exactly equal to the input frequency by 3/4. Exactly means exactly. That is, you can put the comma and then how many numbers you want. And if you, at a given point of your system, have FO and make FO by Q over P, you get again Fi, exactly the same. You see? This is not obtained from a local oscillator. When you have a local oscillator, you can only have a frequency which is plesiochronous, which is not synchronous, plesiochronous to the input. That is, you have an input Fi generated by a local oscillator which is remote, and then there is the channel, and then here you have another local oscillator. This will be never equal to Fi. This will be equal to Fi plus or minus the ppm, 10 ppm, 5 ppm, it depends on the specific oscillator. But there will be never be exactly equal one to the other. Okay? In this case, you have a mathematical relation. There are no ppm of difference between these two. Why? Because this oscillator is not a local oscillator. It is a controlled oscillator, and it is controlled from the input. And so you have exactly synchronism between the two. And even if here you have P over Q, you can always recover the input, exactly the same frequency as the input, by the inverse operation. So these two are synchronous. These two are plesiochronous. These are two really different, very different concepts. This is the concept of a local oscillator. This is the concept of a locked oscillator, controlled oscillator. By a controlled oscillator, you get exactly the frequency that you want. By a local oscillator, you get always an approximation. So if the PLL is properly working, in this case, look here, where you have Fi over Q, and here, where you have FO over P. These two frequencies are exactly the same. If the PLL is at phase lock and there are no cycle slips, and you count here and count here, the two counters give you exactly the same number, even after a time as long as you want. Okay? You can wait for the time that you want. Count here, you will always have rising edge, falling edge, for all the time. While in this case it is different.
It's not clear to me how the phase detector and the low pass filter create the input for the oscillator. Why would you do?
This is the error, and this is the filtered version of the error. This is a voltage controlled oscillator, which is the analog form of the number controlled oscillator. So when the mean value of the error is 0, here you find a 0, and the VCO continues oscillating on the same frequency and on the same phase. And this is the very concept of phase lock. At phase lock, here you will have a 0. Okay? And remember that the VCO is, in the digital domain, z to the minus 1, and then the lookup table for the complex exponential. So when the input to the VCO is 0, here you have a phase which remains, okay, and it continues oscillating at a given frequency, which is the natural frequency of the VCO, plus that phase. So this is the baseband equivalent, in the passband model, the VCO oscillates over his natural frequency plus a phase. This is what happens to the phase. The natural frequency remains the natural frequency of the VCO. So the VCO is cos 2 pi natural frequency plus phi, and in the baseband equivalent you study the phi. This is a property of the VCO. Of course, it must be close. It must be close to this F0. For instance, you want that it is in the holding range, in the capture range, so we are studying the baseband equivalent of. Okay? So basically, we are cancelling this part. And for the rest, this is exactly the same scheme as the number controlled oscillator and the discrete time PLL. Other questions? This is widely used in electronics. Inside an FPGA you can find a number of these circuits. 4, 8, 12. It depends on the size of the FPGA, which are useful to perform frequency conversion, for instance. One example is where you use the digital PLL is the synchronous Ethernet. You know what is the synchronous Ethernet? also called sync key. The sync key is the sync key is well, today my idea was that of making a class on carrier recovery, but technically speaking, this is a basis of communication systems today. Communication systems are synchronized. They are synchronous systems. That is, any radio base has, from the network, a synchronization signal which is the same, it has the same frequency as all the other radio bases that are on that subnet. Okay? And this is obtained thanks to the synchronous Ethernet. In the Ethernet, you have a clock at 125 megahertz. Okay? This clock can be divided to typically to 25 megahertz, which is the typical frequency of the Ethernet. Well, when you pass through the network, for instance, to the backhauling network, that is from the backbone to the access point, to the radio base, the backbone, you have the backhaul, and then the access. Here you have the user. This typically are radio, point-to-point radio. Typically this is an optical fiber. Okay. Here you have, you can have, I don't know, 1, 2, 3, 4 point-to-point radios that brings the signal from the backbone to the user, to the radio base. Together with the signal, this part of the network also brings to the user this frequency, the synchronous Ethernet. And this is 25 megahertz. How to bring the 25 megahertz through the backhaul till the access and vice versa? Well, suppose that here we have a point-to-point radio with a symbol rate that is synchronous to the synchronous Ethernet. That is 25 megahertz by P over Q. That is, you use the QAM, the symbol repetition interval of the QAM, synchronizing it to the input sinusoid, which is in this case the 25 megahertz. And when the clock is recovered, it is also recovered at the synchronous Ethernet. This is for the frequency. Then there is also the possibility of synchronizing the phase of this sinusoid by the so-called 1588, which is a protocol for transportation of the time at the layer, at the Ethernet layer. So by this one, you transport the frequency, and by this other one, you transport the phase of this sinusoid. Suppose that here the point-to-point radio has a clock of 100 megahertz. how can you pass from the 25 to the 100? Or from the 125 to the 100? By frequency conversion in this way. So in this case, this is the clock of the Ethernet, and this is the clock of the radio, 1 over T. The symbol repetition interval. Okay? And this is just an example of the application of the digital PLL as a frequency conversion mean. A way to convert the frequency. Still getting a synchronous frequency. Exactly synchronous, because if this one is 125, this will be 100, and the ratio will be 4 over 5. Divide by 5, multiply by 4, divide by 4. And here the comparison is 25. 25, 25, this is 5, and this is 4. Okay. Basically, here you have links like this. And here you have the access to the user. Together with data from the backbone, this point here, together with data, also gets this clock. Now we want to transfer data and the clock. So when you say 1 gigabit Ethernet or 100 megahertz Ethernet, what do we mean? We don't mean that here you have exactly 1 gigabit of information per second. 1 gigabit is the maximum information rate that can be transferred through the Ethernet. But anyway, somewhere we must have a synchronism which is synchronous with the 1 gigahertz. In this case, the 25 megahertz. Then we can have a bit rate that can be 105, 433 and blah 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 bit per second. This is the actual bit rate. The only constraint that we have on the bit rate with the gigabit Ethernet is that it must be lower than the gigabit. Well, this means that we must have a large number of time slots where to put information. Then we can put or not to put information on that time slot. But having time slots means having a clock reference like this. Time slot, time slot, time slot. We must have 1 giga time slot per second. But this means that we must have also a sinusoid at 1 gigahertz, or a sinusoid at 25 megahertz that multiplied by 40 gives you the 1 gigabit. 1 gigahertz, sorry. Actually, in the Ethernet, you do have 8 parallel channels. Every one of the 8 is 125. So in the end, this is the 1 giga. All these 8 channels are synchronous with the clock at 125. From this clock, the input, you get the 25 and compare the 225. And you transfer through the network this synchronism by locking the physical layer to it. The clock, the symbol repetition interval of the physical layer. Questions? A lot of questions. Now let's pass to the carrier recovery. The model of the input is this one now. This is the input model. A is QIM. W is AWGN. Theta is a random phase. For instance, random phase walk. These models basically mean we have a source, then a channel which basically has up conversion, noise, down conversion. In the up conversion, we have the cos of 2 pi f0 plus theta, theta prime. In the down conversion, we have cos of 2 pi f0 plus theta the second. And the result, theta, is theta prime minus theta the second. So up and down conversion are not exactly synchronized. Why? Because they are based on local oscillators. Note that the difference here I use F0, F0T, and here also I use F0T, but anyway the frequency of the two can be different. It is enough to put this difference into the difference between theta prime and theta second. So this difference can be of the type 2 pi frequency difference T plus phi. The theta can also take this form, okay? And this frequency difference will be the difference between the two frequencies. And also they have random phases, okay? After sampling, we get a model like this. And by now, we don't put the frequency difference, so only the random part, theta k, of the phase difference between the two. AWGN will have power spectral density equal to N0 because we are at the baseband, and we define as usual the signal to noise ratio as Pt over N0, where P is the power of A in this case, and T is the single repetition interval. The power of the wanted signal, and T is the simple repetition interval. For the random phase, we will take the random phase word. So the power spectral density in the Z domain of the phase is represented as usual as gamma to the square divided by the integrator, and it time reverses its Mitchell filter. Now you see, this is not the model of the sinusoid plus noise. Why? Because we are multiplying the sinusoid by the QAM input data. We have studied the model of the sinusoid in noise, and we want to go back to the model. What should we do? Well, simply to cancel data. How can we cancel data? Well, if we know data, for instance, we have a training set, a training sequence, so data are known, we can build an error like this. The imaginary part of A to the star multiplied by the known symbol and by the hat theta, and then take the imaginary part. This is the phase detector that we studied. So here we get X from the channel, A star comes from some knowledge that we have of data, take the imaginary part, and this is the error, hat theta. Then loop filter, the low pass filter, and the NCO. Close the loop. This is the phase detector. Actually, plus the noise. For small error, this is the wanted part. You see, the imaginary part of the complex exponential is the sign of the difference, and for small error the sign of x is close to x, and this is the noise term. This one is noise here. we take only the imaginary part. This is the reason of these two. One half of the total noise. Basically, we have cancelled the phase of the input QIM, and what remains is only the amplitude. So the error is proportional to the phase difference. And the proportionality is the squared modulus of AK. This error is slowly time varying. This modulus is fastly time varying, because at each K we have a new modulus. So at the output of this low pass filter, we cancel the amplitude modulation. And basically we have a smoothed version of the error. A filtered version of the error. Considering that here we have a low pass filter, we can study the expectation of the error given theta minus hat theta. We call this the S-car, S, which is a function of theta minus hat theta. Which for small error, okay, we can normalize here the QIM in this way. Expectation of A equal to 0, expectation of A to the square equal to 1. With this normalization, this S is close to theta minus hat theta. You see, I no more characterize the PLL with an instantaneous input-output. I characterize it with the expectation of the input-output. Why? Because after I have a low-pass filter. So I can look to the expectation. The low-pass filter basically extracts the expectation of. So we can substitute to this error this other one, theta minus hat theta plus m. Why? Because the expectation of this is the same as this one. The only difference is into the amplitude. But I look to the phase. So I can discard basically the amplitude. What I'm doing is simple. It is, I'm taking the imaginary part, which is a sinusoid, and then I'm saying that for a small error, I linearize it. And in place of the argument of the sinusoid, I take the argument of the sinusoid. Then there is an amplitude modulation both on the wanted signal and on the noise. And I'm saying, well, I'm taking care of the phase. So I don't care of the amplitude, even because it will be averaged by the low-pass filter. Questions? Yes, I have a question. What happens when we don't have a training sequence? Because, okay, I have a training sequence, I can use it for starting up for the booster, for starting up the PLL, the carrier recovery. Then at a given time, the training sequence disappears, and I must continue tracking the input phase without the help of the training. How can I do this? Using decisions in place of the non-symbols. Okay? So, demodulation. Oh, no, sorry. I cannot take the decision here. It must be done in 2 steps. Demodulation. Yes, it is correct. Simply, this is. Yes. Sorry. It is like this. Okay. Okay, here we go. Demodulate with the estimated phase. Here you will have A by the phase difference plus the noise rotated. So you can take a decision at this point. This is what you have here. At this point you can take a decision on A if the phase difference is small, and at phase lock the phase difference must be small. In this point you have hat A, this is hat A star by X by the phase difference plus hat A and the noise. So basically, in place of the non-input symbol, you are using the estimate of the input symbol, the decision on the input symbol taken after the modulation. This is the phase detector. Questions? So first the modulate with the estimated phase, then take the decision, then use the decision in place of the actually transmitted symbol, with the idea that both the decision and the estimated phase are good. At this point, take the imaginary part and put it at the input of the low pass filter. This is exactly the same as this one, excepting the A. Here we have the hat A. Here we have the actual A.
There we need a conjugate. And this is the E minus 6K. We need a conjugate to...
Yes, that is, if you have here the theta, put the star and get the minus theta. Oh well, it depends on what you write into the lookup table here. If into the lookup table you write the same thing, but with the reversed sign, then you are putting together these two things. Questions? Other questions? Is it clear the working principle of this circuit? This is called decision directed. Well, this is called data item. The only difference is that you put decisions in place of data.
I didn't understand why in this way we solve the problem of not having the training sequences.
Because if we are at phase lock, then theta minus hat, theta is small, okay? And therefore the signal here is QIM symbol plus noise. If the channel is good in terms of signal to noise ratio, then I can take decisions and use them in place of the training sequence. So I can renounce to the training sequence, or better, I can use the training sequence for the bootstrap. That is to get at first estimate of theta. Then, if I start from an estimate, suppose that at time 0 I have a good estimate of theta, that I have estimated that theta thanks to the training sequence. And then start the decision directed mode. Of course, this system works if the probability of error is small. That is, if hat A equal to A plus decision error with E small. is the assumption that I am making. If the probability of error is large, this means that hat A has nothing to see with A. And so here the phase detector is not measuring the error. The phase detector gives here a good measure of the error only if hat A is equal to A. Remember, look here, this is the imaginary part of this term is the error. So what do we have here? Hat A star by A plus W and then the demodulation. Okay? So if hat A is equal to A, this product is the squared modulus, and therefore this is the measure of the phase error. When I take the imaginary part, I get the sine of theta minus f theta multiplied by a real number. This is only amplitude, but as usual, I am taking care of the phase. The problem is that when hat A is not equal to A, then this term is a complex number with a phase that is non-zero. And this phase affects the measurement of the phase error. You see, it becomes hat A star by A by the difference between theta and hat theta. So everything works if the phase of this term is 0. This means that hat A is equal to A. But if the phase of this term is non-zero, then what I get from the imaginary part is not only the error, is the error plus the phase difference between hat A and A. And this is not amplitude modulation. This is phase modulation, which is of course unwanted. What I want is this. What I get is this plus this phase. Everything works if this phase is 0. Which means everything works if the error probability at the decision is small enough. Questions? Now we said that the error is the imaginary part of A by x by the complex exponential of the estimated phase. Now let's look to the expectation of the error given a certain phase difference. Well, this expectation will depend on the probability of error. Suppose that the probability of error is large. If it is large, here, basically here I'm putting in place of hat A random signal. So multiply the input by a random signal. well, the imaginary part of this product will have nothing to see with the phase error. So the S-curve will be 0. For a small phase error, this is the phase error. Suppose that this is alpha. For a small phase error and high signal to noise ratio, this will be virtually the same as the one before. That is actually proportional to theta minus het theta. For large phase error, suppose that the phase error here is large. The difference between het theta and the theta is large. Do you believe that decisions here are good? No. They will be not good because the constellation will be translated by a phase error. And the threshold detector will make a lot of errors. And so this will go down. And here will be something, let's say, random. This range here will depend on the constellation size. 4 QAM, 16 QAM, 1024 QAM, with constellation with a lot of points, it is enough a small phase error to make decisions unreliable. So this will be, I don't know, 256 QAM, while with the 16 QAM we will have something like this. A much broader range. Why? Because the threshold detector of 16 QAM tolerates large phase error.